Greetings. The alternating series test concerns alternating series, which are actually interesting ones. Their properties are quite interesting to look at because they often involve a slight modification of an otherwise divergent series that becomes convergent because of its alternating series nature. So for example, we could have a harmonic series that is known to be divergent, but when it's transferred into an alternating harmonic series, actually ends up being convergent. So those are interesting facts that we can explore with the alternating series test, because that helps us test for convergence/divergence of alternating series. So first of all, let's look at the general formula of an alternating series, which is something like this. -1 to the n, that makes the alternating fashion behavior, that is what it's caused by, because this -1 for odd numbers will be -1, for even numbers will be positive, so every second term will go up and down, so on. And then it's multiplied by some bn, which is going to be actually the normal function like argument of an infinite series as we're used to it. So for example, concrete example could be, and I can just write it quicker without n equals. I'm doing the -1 to the n over, let's say, n plus 3. And what it means is basically, I can again write it in this form. So what it means is basically, is this -1 to the n, which makes it the alternating series times some normal series, basically argument. So 1 over n plus 3, which could be by itself a normal series. So the whole argument is this whole thing, right? And the point here is that we take this infinite series and we want to see, is it divergent, is it convergent? And for that we use the alternating series test. And by the way, another way, a slightly different way of a general formula for alternating series is also this, -1 to the n plus 1 times bn. How is it different? Well, instead of odd numbers having the minus multiplication, it's going to be now the even numbers having the minus multiplication. It's all just shifted by one unit. One unit in this alternating fashion behavior, but it's the same idea. So let's consider, for example, this example and finish it. Let's see, does it converge or does it diverge? Well, we will actually be able to determine this maybe even quicker than some normal series that are not alternating, because of the quite straightforward fashion of the alternating series test. So what it says is basically, there are some requirements. So the alternating series, let's say in total it is an. An has to be, every term of it, this basically says every term of it has to be above the x-axis, it's bounded below by the x-axis, so it cannot sink into the negative side. So that's the first requirement. And then for it to be convergent, so the only thing that this test tells us is if these two requirements are met, then it will converge. So first of all, the limit of the normal part to infinity should be equal to 0, and also every next term is smaller or equal to the previous term. So it is decreasing, or at least eventually decreasing. That means for some finite number of terms, it can slightly increase, but then eventually it has to get into a direction of decreasing, because otherwise it would not work. So these are the requirements. We need a decreasing, or at least eventually decreasing sequence behind it, so that the terms have to eventually become decreasing, and we need the general term evaluated at infinity or at the limit as it approaches as high of a number as you can imagine to be 0, and then that tells us there is convergence. So we can test it for this one. So basically what is interesting about it is, well, the whole argument, usually we take into account the whole argument when we do a test. But in this case, we know that it's breakable up into parts. One part makes it alternating, and the other part is basically the normal part of the argument. So actually this one will be the one taken into account here. So first of all, is it decreasing? 1 over n plus 3. Is it decreasing? Yes, it is. And by the way, is it above the x-axis for all terms? So we start with 1 and only go higher. This will never be negative, so that's fine. And also it's decreasing because it will only get smaller. And so the last thing we have to check is the limit for infinity. So what is it going to be? N is going to be 1 over a very large number, and that's 0, and so yes, it's satisfied. What that tells us is that this converges. And actually it's interesting, because this by itself reminds us of the harmonic series. It's very similar, just for this 3 that's added there, which otherwise would be divergent as a normal series. Well, actually, this one is slightly smaller than the normal divergent harmonic series, because it has this 3 added in the denominator, but still it will diverge. There's a way to tell that. So that's the idea. We can also apply it with some other example. Another example could be, for example, we could do, it goes from 1 to infinity. Again, n equals 1 could be written 1 over n squared plus n. And again, there should be this. Well, usually it's written in a way that one has to break it up himself. And let me now write this n plus 1 here. So again, expect either minus 1 to the n plus 1 or minus 1 to the n. Both will just make it an alternating series, and this part doesn't matter for our determination of whether if it's convergent or not. So this out of the way, how we can really rewrite it is this times 1 over, and this is the normal part, quote unquote, the normal part. This is the normal part. And now we take care of this one. So again, is it decreasing? Yes, it is decreasing. This thing is decreasing for all terms, 1 to infinity. And then also, does it not cross the x-axis? No, it stays positive. All these terms stay positive. So the remaining part to check is the limit. And yes, again, it will end up so that this converges. So it's a second degree polynomial in the denominator and 1 in the numerator. So it goes to 0 and it converges to 0. So because it converges to 0 at the very high term, it is guaranteed that it will converge. This alternating series as a whole will converge.